Good evening to everyone. My name is Venu from EC. Today I am telling about the counters, a comprehensive overview of counter types, operations applications. In this video, we will cover all classification of counters, types of counters, applications and IC implementation, synchronous and asynchronous counters, special counters, decade ring Johnson, advantages and limitations. Finally, conclusion. What are digital counters? A digital counter is a fundamental sequential logic circuit designed to store a count, the number of times a specific event or process occurs, typically in response to a clock signal. Core properties: synchronized with clock signals, state transitions in a specific order, representing counters in binary or BCD format. Classification of counters: counters are categorized based on how their internal flip-flops are clocked, which scientifically impacts their performance characteristics. Asynchronous counters. These are known as ripple counters. Sequential clocking: only the first flip-flop receive the external clock pulse. Ripple effect. Change of state programmable through the counter. Slower speed. Cumulative programmation delay limits maximum frequency. Synchronous counter. Simultaneous clocking. All flip-flops share on common clock signal. Higher speed. Parallel clocking eliminates cumulative programmation delay. Complexity requires additional combinational logic or control. Asynchronous ripple counter. An asynchronous counter, also known as a ripple counter, is characterized by a sequential clocking mechanism where flip-flops are not triggered simultaneously. Key characteristics: sequential clocking: only the first flip-flop receives the external clock pulse. Ripple effect: change of state prograde through the counter one flip-flop at a time. Simplicity: generally simpler to design and construct due to straightforward cascaded arrangement. Slow speed: cumulative programmation delay limit maximum operating frequency. Ripple counter operations and limitations. Operation: sequential clocking: only first flip-flop receives external clock pulse. Output of each flip-flop receives as clock input for next in flops. Ripple effect: state change is prograde through counter one by one. Limitations: cumulative programmation delay. Accumulate through chain. Momentarily unstable output as clock ripple through flip chain. Timing glitches limit maximum operating frequency. Synchronous counter. Working principle: a synchronous counter, all flip-flops are counted to a common clock signal, ensuring their state changes occur simultaneously. All flip-flops changes state at the same time. Uses combinational logic to control logic toggle inputs. Circuit implementation: for a 4-bit synchronous up counter using JK flip-flop, Q0 always toggle with each clock pulse. Q1 toggle only when Q0 is high. Qt is toggle when both Q0 and Q1 are high. Key characteristics: high speed simultaneous change, synchronous counter advantages, high speed operation, parallel locking elimination, cumulative programmation delay, allowing operation at much higher frequency, eliminated cumulative delay. No ripple effect means all state change occur simultaneously, ensuring stable output, more reliable operation. Concurrent state changes provide predictable and reliable performance. High speed digital systems. Synchronized versus asynchronous. Synchronized counter. Features. Synchronized and asynchronous. Speed higher lower. Delay simultaneous cumulative. Reliability higher lower. Types of counters: up counter, down counter, up and down counter. Up counter increment stored values by 1 with each clock pulse, counting in ascending order, like 0000010100111100. Down counter decrement stored value by 1 with each clock pulse, counting in decreasing sequence. Up down counter combines functions of both up and down counter with control input to determine. Spatial counters. Decade counter. Definition: a decade counter, also known as the mod 10 counter or BCD counter, is designed to count through 10 distinct values, then reset is equal to 0. Key features: counts decimal digits 0 to 9, reset to 0 after reaching 9, provides binary representation for each decimal digit: 000100012001030010, these like and so on 91001. Application: digital clocks, frequency meters, display systems and digital systems. Spatial counters, that is ring counter and Johnson counter. Ring counter, a specialized sequential circuit formed by connecting the output of the last flip-flop in a shift register back to the input of the first flip-flop, creating a circular arrangement. Typically initialized with a single 1-bit circulating through the flip-flop, while the other flip-flop hold the opposite state. An N flip-flop ring counter has an unique state. Johnson counter, a modification of the ring counter where the inverted output of the last flip-flop is fed back to the input of the first flip-flop. Characteristics: produces 2n unique states for an N flip-flop counter. Mod 2n counter, similar to a gray code sequence when only 1 bit changes at a time. Generate specific waveform useful to timing circuits. Sequencing control system: 1 hard code waveform generation. Control system frequency division. Applications of counters: digital clocks, count seconds, minutes and hours to display time. Frequency counters measure signal frequency by counting pulse over times. Generate time delay for event control. Event controls: control product on assembly line on events. Step through memory location sequentially. State machines: control flow in embedded system. Data accumulation, track sampling. Buffers, frequency dividers, reduce high clock frequency. used in an algo digital conversion, IoT devices, data logging with real-time monitoring, automation, process control and management, defense system, counter unmanned vehicle tech, counter ISIS, common counter ISIS, decade counter divider, 4-bit synchronous binary coder, 4-bit down coder. Selection criteria: count range, modulus. Determine the maximum count value required in n-bit counter has a maximum module of 2 power n. Ensure clock frequency. Ensure the ICs and operate reliability at the required input clock frequency. Synchronous counters support higher frequencies. Power consumption. Consider the power budget, especially for battery power designs. Some ICs are designed for ultra low current consumption. Output format. Decide whether the output needs to be in binary BCD or another format. BCD output are useful to human reliable displays. Advantages and limitations. Synchronous counter. Advantages: simple design with straightforward cascaded arrangement. Lower component count resulting in lower cost. Limitations: a programmation delay affect maximum operating frequency. Sequential triggering introduces timing issue at high speed. Synchronous counter. Advantages: faster operation with simultaneous state change. No cumulative programmation delay or ripple effect. Summary. Key takeaways: counters are fundamental sequential logic circuit using flip-flops to store and count events in response to clock signals. Asynchronous counters offer simply but suffer from propagation delays, while synchronous counter provide faster, more reliable operation. Various counter types: up, down, special, servo specific applications in digital systems. Counters find essential applications in digital clock, frequency measurement, industrial automation, and, and, and advanced control systems. Thank you.